Looks like we're live. Hello everyone and welcome to yet another recreational programming session with Mr. Azozin. Let's make a little bit of an announcement and officially start the stream as usual, live on Twitch. And what are we doing today on Twitch at .television website? Today we're checking out QBE language backend, right? So I'm gonna give the link to twitch.tv/Soding, the place where we're doing all that, and I'm gonna ping everyone who's interested in being pinged. And there you go, the stream has officially started. So on the previous stream we checked out a programming language called Hair. All right, so it's a very simple programming language, like it's a C-style programming language. And one of the notable sort of like feature of that language is that it uses QBE backend. Right, for those who doesn't know, like languages are usually split into two parts, like a front end and a back end, almost like web applications, right? So, but in case of web applications, front end is running on your machine and back end is running on somebody else's machine. In case of compilers, it's like it's part of the same application that is running on your machine, obviously, right? So, and essentially, where lies the front end and where lies the back end, this particular line can maybe shift around, right, so to speak. But essentially by the front end, we understand a thing that parses and understands the language, right? So you have a text file with a program written in a particular language, and the front end just lexes it, right, splits it into tokens, parses it, constructs an AST, right, abstract syntax tree out of that thing, and then it traverses that AST, maybe does some transformations, maybe something like syntax desugaring if there is a syntax sugar and stuff like that, and then traversal of that stuff and generates, intermediate representation, right? Intermediate representation that is usually handed to a backend. And the backend takes that intermediate representation, applies some optimizations, and generates the final machine code, right? So usually these kind of parts are developed separately, quite often by different people, right? So there's people who specialize on like developing only backends, and there you go. Here is the compiler backend, right? So essentially, it accepts an intermediate representation of your program in the form of a text itself. Right, so by itself, it is a small programming language already, right? So, and then it applies optimizations and generates assembly, right? And then what you do with that assembly, you essentially take that assembly and construct an executable. So, and this is very small and very not that known backend that I discovered only because I checked out this programming language. The most popular backend, right, like the one that everybody knows about, is probably LLVM. You probably heard about this one. Right, so LLVM compiler infrastructure. It's not even a backend, it's an entire compiler infrastructure. Right, so there's something with the website. So I'm using basically like a built-in dark reader feature in Chrome. Right, there is a special experimental flag, somebody told me on Discord, and sometimes, as you can see, it fails. Right, LLVM, like a lot of modern languages use LLVM, like Clang, the C++ compiler uses LLVM, Rust is using LLVM. Right, a lot of newer languages, like I think Zig uses LLVM, maybe Odin, I'm not sure about that. So all of these modern languages uses LLVM. LLVM is basically the React of compilers, right? It is basically the React of compilers minus the toxic community. Right, but the downside of this particular backend is that it is very, very huge. It is extremely bloated. And it's a huge dependency. In my opinion, it has to be justified. Right, so it has to be justified. And if you're developing like a hobby small language, depending on LLVM is kind of too much. It's kind of too much. I developed hobby small programming languages, and not only I didn't use LLVM, I basically created my own small backend that doesn't even do any optimizations or anything like that, right? Because you don't need optimizations to make your language work, right? If you're trying to make a working language, you don't need optimizations to make it work. Optimization is not a necessity, it's a luxury, right? It's a luxury. And that's one of the reasons why people program in Python, right? So because nobody really gives a shit, right? So that's why web is popular, because nobody gives a shit, right? So it would be nice, right? So if things were fast, but it is what it is and it isn't what it isn't. So I think QBE in that regard stands somewhere in the middle, right? So essentially they even stated themselves in their marketing, right? It's a compiler backend that aims to provide 70% of performance of industrial optimizing compilers. And we know what they mean. Industrial optimizing compiler, we know what they mean. What they mean in LLVM, right? They're talking about the LLVM, right? In 10% of the code, 10% of the code. 10% of the code. QBE fosters language innovations by offering a compact, user-friendly, and performant backend. The size limit constrains QBE to focus on essential and prevents embarking on a never-ending path of diminishing returns. So yeah, and essentially that's what I want you to do today. I want you to check out this backend, right? Maybe like directly programming it, because like this backend is straight up its own programming language. Right, it's straight up its own programming language. You can program in it, right? So I do not understand shit by looking at this text. What the fuck is all of that? It's worse than PHP, but we can try to program in this thing. And maybe if we'll have time, maybe we can write a simple programming language that generates this backend, right? And see how it goes. So essentially, I want to put this thing under sort of like my tool belt, right? So essentially, if I want to quickly develop like a simple language, I know that there is such thing as QBE, and I should be able to quickly pick it up and just prototype something. So yeah, that's basically the idea for today's stream. Sounds good, sounds Gucci, sounds Atamaguchi, and let's go. So let's acknowledge the subs. Thank you so much to Cube a lot for 2 months. Let's go subscription. Thank you so much. Thank you. Coraner, thank you so much for 2 months subscription with the message LLVM season. LLVM season in coping right now. So yeah, thank you so much, Koi Quarter, for tier 1 subscription. Thank you. Rest in peace, LLVM both. Why are we? Okay. We're burying LLVM already. I mean, LLVM is not going anywhere. Right, so all of that is just a clickbait title. Come on, this is Twitch, right? I'm a streamer, like, you know what to expect from me. So, but I mean, it's a cool alternative nonetheless. It's a cool alternative in my opinion, right? Especially if you don't want to deal with LLVM. And to be fair, like recently, a lot of people started to complain a lot about LLVM, right? So about its documentation, about how, you know, bloated it is and stuff like that. And it's just like people are trying to slowly kind of move away, like kind of distance themselves from LLVM. And yeah, so this could be like a good alternative in my opinion, at least for myself, right? At least for myself. I know that not everybody masturbates to simplicity as much as I do, but it is, and it isn't what it isn't. Okay, good. So we already have QBE installed. Right, so I already do in fact have QBE because I installed it from the previous stream. So I think I'll need to put the description, link to the previous stream in the description, right? Link to be done, link to here stream. So this is where we install QBE, so I'm not going to spend time installing it. And I think it would be fair to actually include LLVM in the description as well, right? So as a comparison of the popular, you know, popular backend. So what we're gonna do in here, so we already have a here folder where we have the source code of QBE, but maybe I'm gonna actually go and create QBE folder, right? So let's try to maybe create some sort of a hello world. So essentially, we create a function like this. Right, we create a function like this, and we start the function with the word function. So let's actually do something. I remember that the extension is called SSA, right? So the extension is called SSA. So this is a function. And because of that, let's actually set the highlighting to JavaScript. Right, it doesn't even work. What is this? Where is my JavaScript? Yeah, there we go. So this is going to be JavaScript. So we're programming in JavaScript now. Actually, it's more like PHP, right? So can I do PHP mode? Yeah, so PHP is a little bit better because we're going to be having like these percents and not percent, but dollars and percents and stuff like that. I'm really curious, what the fuck is W? What the fuck is W? Is that type? It could be the type. So my hypothesis as of right now that W means word, right? So essentially like whatever the size of the word of the current machine. So on a 64-bit machine is probably going to be 64 bits, on a 32-bit machine is going to be 32, right? It's the current word, sort of speak. Right, so we're going to do the word. So the name starts with percents. PHP mode actually works really great with this, right? You know your backend is good when it can be easily highlighted with a PHP mode. You know your backend is good. Right, so we accept two words, the A and B. And essentially, it's kind of interesting. I just had this thought, like, why in old languages especially, why there's always a prefix in front of either a function or a variable, and sometimes there are different prefixes, because obviously just by observing this language we can see that dollars probably mean function name and percents probably mean a variable name, right? Like, what's the point of doing these prefixes exactly? Because a lot of modern languages just don't do that, but all the languages like to do that. And if you ever implemented a language, by the way, even in interpreted one, you probably know the answer. It makes it easier to actually look up that specific name in a correct place. Right, that specific name in a correct names. Parsing, it depends, probably not. I wouldn't call that parsing actually. It's more like a semantical analysis, right? It makes it easier to do semantical. What the fuck is this shit? Okay, disable logging, fuck off. So yeah, it's more like a semantical analysis because, right, if the name starts with dollar, I know that I need to look up this name in a table of functions and not in a table of variables. In a table of functions, not in a table of variables. Because obviously they're going to be in separate tables, probably. And if you don't have these prefixes, what you have to do, you have to check, okay, let's check that in a table of functions. Okay, it does not exist in a table of functions. Let's check it out in a table of variables. Okay, so it does exist, so that means it's a variable. Right, and because of that, you can actually have separate namespaces for different kinds of names in your language. Different kinds of name of the language, right? So if the kind is function, you look only in that table. If it's a variable, you look in another table. And because of that, you can have functions and variables with the same name, and they are distinguished with this prefix. So this is kind of stuff that kind of makes sense if you're developing the language, but doesn't really make much sense when you're programming in that language, right? You don't really see these internals, right? So it only justifies something internally, so to speak. But this is just like my opinion. This is how I see that, because I implemented like a few languages, and every time I was implementing few languages, I was kind of thinking that if I had some sort of a prefix, it would be kind of easier to distinguish these kind of things super quickly, if you know what I mean. And of course you can actually keep all the names in a single table and do some sort of a polymorphism. You can basically tag different kinds of objects with different tags, right? So you can have unions, or if you are into OOP, you can have an abstract class, right? So you can have an abstract class, and basically for different kinds of objects you can have different implementations. So people in the chat say that that's exactly what they did. So yeah, basically table with the tagged unions and stuff like that. So yeah, there are both approaches. I think I used both, right? So to be fair, maybe a single table with different kinds of projects is a little bit easier, because if you have separate tables, it's just like you have to check sequentially. And if you add a new kind of object, right, you have to visit all of the places where you sequentially check all of the kinds of objects, and it's kind of like a mess. Anyway, so yeah, we created a function. So the next thing we have to do, right, so we adding these two variables together. I suppose this is sort of like an instruction, right? This is sort of like an instruction. So you cannot really write mathematical formulas in this language, right? You cannot just do things like a multiplied by b plus 32, right? You literally probably have to split it into sequences of these operations, almost like an assembly, because this language is slightly higher level than assembly, right? So, and it is responsibility of your programming language to actually parse the expressions and generate all of these sequences of instructions, right? So, and here what we do, we actually assign it to C. It's interesting how I don't have to really declare anything in here, so it does all of that automatically. And I simply then return that C. I simply return that C. So that's pretty much it, right? So that's pretty much it. We also have to denote a start in here, and I'm not really sure what start means. So far, everything kind of makes sense, except the start. And I would assume that maybe it's an entry point of the program, but start exists for each function. And you may say, oh, it denotes the start of the function. Okay, but isn't this supposed to denote the start of the function? Like, like why? Maybe you can have some code that is before the start of the function. So I don't know. So far it feels like an extra syntax, but maybe I just don't understand something. Maybe I just don't understand something. So the next thing we have to do, we have to create the main function, right? So we have to create the main function. We have to do export function because this backend is also developed by JavaScript developers, right? So you have function, you have export function. And this time we're doing a main, right? So, and this is probably going to be the entry point, right? So this is probably going to be the entry point. And apparently, right, so this is how we call this function, right? So we do add, we say, we pass word 1 and word 1 again, then we just call it like so, right? And all these prefixes probably are needed to indicate the type of the sort of like a literal that we have in here, right? So we indicate in the type of the literal. Sure. So then we're assigning result to that, and then we call to printf. So we then use lfmt, right? And as you can see, fmt is the data, right? You have functions and you have datas. Right, you have functions and you have datas. So, and they use L in here, so which is probably analogous to W, right? It denotes the type that we're interpreting this thing as, right? It denotes the type that we're interpreting this thing as. So, and essentially we define the data like this. This is actually a pretty cool syntax, right? So you have like functions as objects, so they hold code. Functions hold code, and data holds data, right? So, and B denotes that this is a sequence of bytes, so you can use string literals to denote sequences of bytes, and sometimes you can just do extra bytes. It feels like a FUSM, right? It feels like FUSM, right? Because in FUSM, you can also do similar things. So if I do something like FUSM, maybe like this, right? You can maybe have hello, right? And you can say db, so that will allocate the bytes, and you can have hello world in here, and then you can say 0, right? And all of that is just like a one sequence of bytes with a 0 at the end. So I think it is kind of analogous to that, right? I feel like. Now we have to put this thing probably to indicate that this is a variadic function, right? So we're sort of like, this is my hypothesis. I don't really know. I haven't read the documentation of this thing yet, but I think we are indicating that this is a variadic function, and because of that, the things are passed like via the stack or something like that. But as far as I know, even variadic functions in C follow the, like, you know, x86-64 call convention, but whatever. So, and we're passing the result of the add function in here, and then just return 0. Okay, so far I understand pretty much everything except the start, right? I don't really understand what's up with that, and not fully understand how this particular syntax works. But apart from that, it's pretty straightforward, right? So you can even program in this language directly, manually. Why not? You may say, oh, it's too low level. You're not supposed to program in a low level language. I mean, I program in assembly just fine. Skill issue, dab, dab, dab. Right? Yeah. So anyway, now we need to actually generate assembly out of that, right? So let's go ahead and generate assembly out of that. We can do QBE, and we're going to provide this thing. There we go. So it kind of worked, but then it says invalid class specifier. Okay, so that's kind of weird. Oh, this is because when I'm assigning, I'm supposed to say W, right? So what kind of assignment I'm doing, right? So I'm doing an assignment of the size of the word. Right, if I try to do it one more time, there we go, it generated actually assembly, right, and we can clearly see, so this is add function, and it's kind of cool that it used registers in here, right, it just, yeah, it directly used registers, so, so we passed stuff from, yeah, so it probably accepted the first parameter via RDI, right, then moved it into EX, and then just added to RSE. Actually, it goes like this. So, right, it added to that, and then added to that, and through racks, it returns the entire thing. Okay, that's cool. It even used leave, right, which automatically sort of restores the stack, I suppose. Yeah, I think that's what it does. And then it generated the main, and then it generated the data. So that's pretty cool. So you can actually specify like the name of the file into which it's going to save assembly. So I think we can do something like this. Right, so going to O main S, right, and if I open S, that's basically the assembly. So maybe we can even create the make file, which is going to do all of that. So it's going to be main S, main SSA, QBE, O main S, main SSA. And if I try to make this entire thing, right, as you can see, it does in fact compile. So, and after that, we can just generate a program out of that, right? So let's actually say that we depend on this thing, and we're gonna do this thing. So CC, I suppose, will automatically use the assembler compiler when it sees the extension, right? So, and let's actually try to do that. Okay, so it generated the final thing, and we've got the final executable. We can take a look at what it does, right? So this is basically elephant stuff. Doesn't really have debug information. I wonder if you can make QBE generate debug information, but that debug information is probably going to be part of the assembly. I don't really know how exactly it works, but anyway. And we can now try to run this entire thing. 1 and 1 make 2. So yeah, that's basically it. Right, so far so good. So you can program in this thing, right? So you can actually program in this thing. And if you take a look at what kind of executable that is, it is still dynamic executable. I don't really know how to make static executables with this kind of stuff. Right, but yeah, you can just use it as an alternative to C, but it's actually rather low level again, right? So you probably don't have mathematical expressions in here, right? Because your language is expected to actually do that. Your language is expected to parse all of the mathematical expressions and then generate the code out of that. Okay, so let's actually take a look at the docs. So quick comparison to LLVM. To be fair, I don't really know LLVM, so for me comparison to LLVM is not going to be that useful. So I'm probably not gonna read that. So let's take a look at the actual documentation. So you can have basic types. So what do they say? The intermediate language is a higher level language than the machine assembly language. We already noticed that. It smoothes most of the irregularities of the underlying hardware and allows an infinite number of temporaries to be used. An infinite number of temporaries, as opposed to like temporary variables, because every time you assign something, you kind of create like a temporary variable. By the way, so the language is based on something called SSA. Right, so it's based on something called United States Social Security Administration. Yeah. Compiler. So can I just do, yeah, maybe on Wikipedia. Maybe Wikipedia also will go to security thingy. So it's a static single assignment form. Right, it's a form of intermediate representation that looks like this. Right. So actually, I think it looks like this more or less, right? So essentially, it's a sequence of assignments of things. It's a sequence of assignments of things. And you are allowed only to make one single assignment. And if you are modifying a variable, you sort of like denote the version of that variable like with a number or something else, right? And from what I understood, it simplifies some of the optimizations, right? So it simplifies some of the optimizations. For instance, like this is a, I suppose, classical example, right? This assignment is useless, right? This assignment is useless, but for a computer, it's kind of difficult to figure out that this assignment is useless. But if you allow only one single assignment and basically denote different versions of the variable with like some sort of a number, it is very obvious that one of the variables is never used in here, like y1 is never used, so you can easily eliminate that. So it's yeah, everything is like shadowing or something. Yeah. So yeah, I suppose, and as far as I could understand, it has also like number of useful properties, and that's why compiler developers really like this kind of thing. I never worked with that, right? By the way, I never worked with that. All of that is very new for me, and that's, by the way, why I'm checking it out, because maybe it's going to be useful for me in the future. Right, so maybe I'm going to develop my own compiler backend that uses this kind of stuff. So I'm trying to learn something new, if you know what I mean. I'm trying to use something new. John doesn't seem to like SSA. Well, good for him. That means he knows like what is SSA and how to use it and why it doesn't work for him. So I'm really happy for him for all of that, right? So I don't know what is SSA. I don't know how to develop it, and that's why I'm learning it, right? So maybe after learning it, I will come to the same conclusion, right? So because the way I usually structure my intermediate representation, I basically develop a stack-based machine, right? My intermediate representations usually just basically stack-based machines. And it's kind of a dumb way to do that, right? But it kind of works for me for now because I don't know any better. So maybe I will learn something better. We'll see, we'll see. So anyway, I'm going to put this thing in the description, right? I'm going to put this thing in the description, and let's maybe continue. Let's maybe continue. Right, so input files. Okay, that's pretty cool. The intermediate language is provided to QBE is text. We already figured it out. So here is the complete hello world. Right, in the hello world we have a data with hello world. We just call to function puts, and that's about it. BNF notation, I'm not really interested in BNF notation, right? I'm not a machine, I'm a human, so I would rather prefer like examples rather than like a formal description of the syntax, right? Because it's kind of useless for me, and it is useless for the majority of the people, except maybe the, you know, language developers themselves. Sometimes it is useful, right, when you want to check out like specific concrete situation, but when you're just learning thing, the examples are usually better. So we have simple types, right? So we have base type word is probably long, short, double word, probably, I don't freaking know. Extended type. So extended type are one of these things, and also B and H. Okay, so there's no description in here what they mean, but there is a description in here. So the intermediate language makes minimal use of these types. By design, the types used are restricted to what is necessary for unambiguous compilation to machine code and C interfacing. Okay, so making more complex types like structures and arrays and stuff like that is actually kind of up to you, up to the language. So what they provide basic types and an ability to maybe like allocate like memory, and within that memory it is your responsibility to actually sort of parse the layout and have more complex types, if I understand that correctly, which is good, right? So which is good. So they provide the bare minimum to smooth out the differences between the hardware, right? So W is a word, L is long, S is single, right? So D is double. I suppose these are floats, right? Yeah, this must be floats, by the way, single and double. So they stand for effectively 32 integers and floating points. Yeah, there we go. There are no pointer types available. Pointers are typed by an integer. This is exactly what I'm talking about, chat. Pointer is just a fucking number. There you go. Look underneath the language. Look. It's crazy. Fucking no. Thank you. So it's just a freaking number. Memory is just an array of bytes, and pointer is just an integer. So anyway, there are no pointer types available. Pointers are typed by integer type sufficiently wide to represent all memory addresses. Right, temporaries in intermediate language can only have a base type. So in temporaries, I suppose, are these things. So extended types contain base type plus b, byte, and h, half of a word, respectively for 8 bits and 16 bits integers. They're used in aggregate types and data definitions. So aggregate, oh, wait, it does have structure. Wait, it just like has structures. Like, why do you need a higher language then? Like, you can program in this shit already. Like, why? What? So how is that different than just generating C? It has structures. What's next? It also has unions. It's a full-fledged language. Like, what's my job then? I don't freaking know. They're used in aggregate types and data definitions. Okay. For C interfacing, the intermediate language also provides user-defined aggregate types as well as signed and unsigned variants of the subword extended types. Read more aggregate types and function section. Though maybe intermediate language, being aware of sort of like structures and everything, is very useful for, you know, x86-64 call convention, right? Because x86-64 call convention on Linux is kind of anal. It uses like a very specific algorithm to figure out what goes into registers and what goes into stack, right? So essentially, if you have a structure, so, and we actually encountered that. We actually encountered that when we were interfacing to raylib through assembly, right? Let me actually go to the C mode. If you have a structure that looks like vector2, right, and it has two components like float, x and y, and then you pass this thing to a function, right? So you have a function that basically accepts this vector. So this vector is going to be passed via a single register, this entire thing. So both of the floats are going to be put into the XMM like 0, right? Both of them. So an entire structure, if it fits into the register, it's going to be passed via the register. So for intermediate representation, if it supports this call convention, it probably needs to know like a little bit about how structures are organized and stuff like that, so it can make a decision on how to pass this kind of stuff via the register or via the stack and everything. Because as far as I know, this intermediate language kind of does all of that job for you, right? So it figures out the call convention for you, so you don't really have to think about it, right? So you just pass things around and that's about it. Right. So, subtyping, this motherfucker even has subtyping. Okay, oh, for primitive types, right? So intermediate language has a minimal subtyping feature for integers types only. Any value of type L can be used in W context. Okay, so in that case, only 32 least significant. So L can be used in a W context, but isn't L bigger? Isn't L bigger? Wait a second. I'm pretty sure I saw long, yeah. So long can be used in word context, so it's automatically converted, so it's cutting them. All right, so that's a bit weird, but I mean, okay. So subtyping. So it can be used in long context. All right, so you have constant values, you can have constants in here, and there you go, you can do subtraction, you can do add. I would like to have like a reference of all of these operations that it supports. So you can also have, you know, linkage, right? So you can link with things. So section init array or something, definition, aggregate types. So yeah, here are the aggregate types. You can have like tuples or something. So this is a union types, right? You can have functions. So far so good. Load W, you're reading. Oh, this is a very interesting syntax. Okay, so this is okay. So we define a type, we pass this type like this, and then we essentially just use it as a pointer. So we're loading, and yeah, okay. So add byte. This is very cool. They're using different interesting instructions, and I think there should be a reference guide of all of the instructions that you can use, because, okay, so instructions. Instructions are a small piece of code in the intermediate position to form a body of the blocks. Okay, so yeah, because it's cool that you use all of them. What's the list of all of them, so I can see? So there's also jumps and everything for control flow. So you can jump to identify. So this is blocks. So I suppose, okay, so I suppose that's basically the list of the instructions, right? So they document it in these sections. Okay, so you have a section of memory, and in the section of memory, here are all of the instructions related to memory, right? Store this thing, then load these things. Okay, so there's also bleed. Instruction copies in memory data from its first byte section, and oh, this is actually pretty cool, right? So it's like a mem copy, right? So all of the instructions for copying. So comparison, conversion, casts. So this is a call. So you can work inside with variadic, right? Inside of the body of the function. Right. So this is C, I suppose. Few instructions are specific to SSA form, some sort of specific instruction. Okay, so the instruction index, here it is. All right. So, okay. That looks good. That's basically the entirety of the intermediate representation, isn't it? So that means I know everything, roughly. I kind of skipped the part about the compound type and like their specific and stuff like that. But I mean, is it really that important? Is it really that important? Yeah, I guess that's basically it. So I really like that. Just like you can basically skim through that and get an idea of how this entire thing works. And also, it also gives me ideas for some of my you know, languages in the future. So. There are users, right? There are users. So, oh, they actually featured here. They actually featured here in here. cproc is a comprehensive C11 front end for QBE, right? So somebody actually implemented a C compiler using QBE. Damn, right? This entire community, like, of people who develop these things, are just like very freaking active. So there's SCC. Damn. I kind of want to maybe write like a simple language, simple programming language that uses this thing. But I need to define like a scope for this language, if you know what I mean, like a scope, because if I start implementing language, it's probably not going to be like a single stream, right? So what kind of a simple language can we implement? Right, that will fit within the stream. So a new port, I don't know, like we can try to do that, but we can implement a simple port, why not, right? So it's just like, but the thing about ports is that it kind of assumes like the stack-based machine. This is not particularly stack-based machine, but essentially if you have the following language, right? So let's actually do the text mode. right, you do 1, 2 plus, and then you like print this entire thing. How would you even create, like what can you even generate in here, right? So you generate a function w main, something like this, right? And you're supposed to put start in here. And every time you push like an element on the stack, every time you push an element on the stack, what effectively you're doing, you're creating a new temporary variable, right? So we can say, okay, so S1 is going to be 1, right? So this is this how we do that? I'm not really sure. So we pushed the first thing on the stack. So the stack will consist of temporaries, right? So the stack can consist of temporaries. So then we push 2 onto the stack, right? We push 2 onto the stack, and then we do plus. So effectively what we're going to be doing, so by the way, I think this has to be like this thing. We do S1 add S1 S2, right? And after that we are just doing call printf, so maybe something like fmt integer, right? So it's specifically for the integers, and what we're doing here, we're passing this thing on the top, and obviously then we just return like 0 or whatnot. I think that's how we do that. So return, let me find documentation, because I'm starting to forget the syntax, but I mean I just learned the syntax today, right? So I think it's yeah, you can just do return 0, you don't really have to do that. And then if I'm assigning something, right, if I'm assigning something, can I just assign like do I have to provide this thing like that? I don't think I have to, right? So because I already say that it's going to be word assignment, so I can just do it like that, right? I don't think it is necessary, right? And essentially, like, this is what you would generate out of this code, right? So this is what you would generate, which sound reasonable, right? So which is pretty reasonable. We can try to implement something like that, right? So that's pretty cool. That's pretty epic. But something even more interesting would be to write a compiler that understands something like this, right? So that takes this expression and then generates this out of this expression, right? So, and that will require implementing something like a prot parser, if you know what I mean, right? So prot parser, is that how it's called? Prot parser, yeah. Wikipedia. So this is something that, yeah, this is something that John recently talked about, right? So prot parser, we can go into that. Implementing prot parser is not really that difficult, so we can spend some time doing that. Right, so I can put that in the description for anyone who's interested. And yeah, so let's actually implement a compiler that understands this kind of thing, right? That understands this kind of thing. I think it's going to be kind of interesting. So let me kill that. And so here is just like a hello example. I would like to maybe call that hello example slightly differently. Right, so 1 plus 1. Right, so let's actually call it 1 plus 1, because literally what this thing does, it just adds together 1 plus 1. So I wonder which mode is better. I think JavaScript mode actually highlights this thing way better. I think it highlights it way better. So we're going to be using a JavaScript mode for highlighting the QB intermediate representation. Right, and in here, where is the make file, I'm going to query replace main with 1 plus 1, boom. And I'm going to rebuild this entire thing. Boom, there we go. So we have 1 plus 1 example. I don't want to remove it because I think it's a pretty good example that we can refer to. And the next thing we can do, we can just try to implement the compiler, right? So let's actually call compiler. So what we're going to be doing, we're going to be using C, right? So let's actually go ahead and do that. 3 months best inspiration to true enjoyment of programming. Thank you. I'm really glad that people find, you know, find the enjoyment of programming again by watching my streams, because that's kind of the goal. The reason why I even started to stream in the first place is because I got so demotivated with the office job. It sucks out all of the enjoyment of programming from you. It literally kills programming for you. So at the time, right, so I was working my office job and I discovered streaming, and I realized that when I stream and do whatever the fuck I want, I remember those times when I only discovered programming and actually enjoyed it. And I really want to preserve that. I think it is very fucking important to not forget why programming is enjoyable. Because if everyone forgets that programming is enjoyable, well, the industry might die. The entire industry might die. So I believe my purpose in the world is to be the keeper, the preserver of that enjoyment that people forget over time. Right, and people forget over time not because they're getting old or anything like that, but because of the office job. Right, it sucks out all of the enjoyment of programming, and it is very dangerous. Right, it is very dangerous because, again, if we don't enjoy programming, we may stop doing it, and if we stop doing it, well, all of our infrastructure depends on programming, on software. So it is important. It is important. I do actually believe that whatever I'm doing is important. I work in a startup, so it's pretty fun creating new things. Liberty is given in startups. I actually never worked at startup, to be fair. I just realized that. I never really worked at startup. Maybe I should give it a try. Maybe I should give it a try, because I worked a lot in like this huge corporate enterprise, you know, companies, and that's kind of the perception of you know, real programming that I've got, right? So, and that's why I absolutely fucking hate it. So maybe I should have tried different kind of programming, right? So I already tried recreational programming on streams. Maybe I should give it a try to startups at some point. Maybe. All right. So let's go. So what we probably want to do, we need an ability to read the file, right? We need an ability to read the file, and as always, we do that through knob, right? So which is a, you know, a special library and the build system that I use all the time, right? So let me find the knob.h. And since I'm going to be using knob, I might as well actually like use knob instead of makefile. But we'll see how it goes. We'll actually see how it goes. I'm not really sure. I just don't want to break my flow. Don't want to break my flow, and just do that. So implementation. Right. So the thing about knob is that it has a cross-platform function for reading entire file. Right. So there was a read entire file. So there we go. So here is the function that we need. And so essentially we can have the input, right? So this is going to be input. And how should we call, you know, what's going to be the extension of that language? What's going to be the extension of that language? Because the language looks like this, right? So we need to somehow compile these things. So let me actually come up with the with the expression that we want to compile. 35 plus 17 multiplied by 2. Right, so to be fair, this looks like Python, so let's actually... We're gonna be making a Python compiler, holy shit, yeah, so let's actually do it like that. So we're gonna be making a Python compiler, we're gonna compile subset of Python. How about that? How about that? I mean, it's a... We can actually make a legit Python compiler, but for a small subset of Python. It's a subset of Python, right? So you can take an official Python compiler, interpreter, I mean, run it, and it will work, right? So, and then compile with our compiler. So, I mean, it's a subset, all right? So, it's actually pretty cool. Such a dumb idea, but I mean, So is my entire channel. So main.py, so we take that, and it's gonna be path. And let's actually put this stuff in here. We're going to be allocating the builder, and we're going to be reading all of that into la builder. And if this entire operation fails, we're going to return with non-zero exit code, right? So with non-zero exit code. So let's do nob log, nob info, and we can say, so contains this amount of bytes, right? So we can say path contains SB count amount of bytes. All right, so let me go to make file, and we're gonna have a compiler C, and let's just, you know, compile it. We're gonna be compiling the compiler, and let's actually make it. Okay, so that seems to be working, and if I try to run that, it says that main.py contains 17 bytes, and it is in fact true. It contains 17 bytes. That's pretty cool. So the next thing we need to do, we need to tokenize this shit. I have written so many goddamn tokenizers. Do I have to write it again? Usually writing a tokenizer takes a lot of time, but maybe fuck it. Let's actually take the C tokenize. Nothing says to be, right? I'm reaching the levels of efficiencies never seen before on Sodium channel, right? I'm literally reusing all of these components, right? So Lexer, the backend and stuff like that. But here is the thing. The difference between me and those web devs is that I understand how these components works, and if I need to, I can implement them. Right? It's just like I don't want to. So yeah. So it's the same like with the Raylib. People think that I'm such a fan of Raylib. Oh, look, I'm a Raylib fanboy. But the reason why I like Raylib is because I can implement it. So the thing is, like, if I were to implement, like, you know, the library for graphics that I can reuse, I would pretty much end up with a similar thing. Maybe a little bit more complex API, but I'm gonna end up with pretty much the same thing. So the only reason why I don't do that is because I can just use Raylib, because it's like almost exactly the thing that I would do. So, you know what I mean? Right. So that's the reason. I like to use things that I understand. To be fair, granted, I do not fully understand QBE, but I'm in the middle of learning it, so maybe I'll just learn how to use it and try to implement something similar. Okay, so what we need to have a Lexer, right? So there's a C Lexer, and we're gonna reuse that thing. Hopefully, I already used it one time, but I forgot how to use it. I forgot how to use it, so let's actually grab that, and there we go. So wget, and let's include the STBC Alexa, play Despacito. So implementation, right? So you have to include this kind of stuff, right? So let's define implementation. For those who doesn't know, it basically instructs the header to act like a C, right? So if you never encountered like header-only libraries, so this library, this single file, acts like an entirety of the library. If you just include it, it acts like a header file. That means it doesn't contain any implementations. If you do define, it also includes implementations. The reason why it is done like that is so you have control where to put implementations, so you can actually include the header as many times as you want. Right, so every time you include it, it will only include the declarations, but then through this macro you can also control where you put the definitions, so during the linking you don't have the linking conflicts because of the several implementations of the same thing. Right, so that's basically what it is. Anyway, so I forgot how to use this goddamn Lexer. So there is a huge structure, I do remember that, there is a huge structure called STB Lexer. Right, so here it is. So let's go ahead and create the Lexer. So I'm going to call it L, and I'm going to 0 initialize this entire mother flipper, right? So there we go. We allocated it on the stack, and it is in fact initialized, right? So the next thing we have to do, we have to call the initializer. We have to call le constructor. So we have to pass the pointer to the lexer in here, right? So here is the pointer to the lexer. So then we have to pass the input stream. The input stream is located in the string builder, so we can say here it is. Then we have to supply the end of the stream where it ends. We don't really have the end of the stream, but we do have the size of the stream. So we can turn it into an end by adding to the beginning, right? And there we go. So this is where the end is located. Another interesting thing that this lexer accepts is the string storage, right? It is a string storage. So essentially when it parses string literals or stuff like that, it may allocate a little bit of memory, but it's going to be allocating it in a temporary buffer, and you are the one who allocates that temporary buffer for the library. So let's actually do that. I don't know. So I'm going to actually put it like this in here, and we're going to just malloc it. So how much we want to allocate? So that should be enough for everybody, right? So that should be enough for everybody, I think. So we might as well even put something like store in here. So this is going to be store, and that's essentially the size, store length. So we also want to assert that the store is not null, right? So malloc didn't fail because malloc does not fail, right? It didn't fail because it doesn't fail. So, and that's why we're asserting it. And there we go, we initialized the lexer. Oh, it's actually 40, I'm sorry, I forgot the meme. Thank you so much for correcting me. Thank you so much for correcting me. SB items count -1. Usually, okay, so the common sense tell me, right, quite often in computing, you have two ends that denote sort of like a sequence in the memory. Begin usually points at the first element, and end usually points at the element after the last one. So that's the usual sort of convention that we have in here. The reason why it is like that, it is super easy to calculate the size of the sequence by just doing this. Because otherwise you would have to do +1. But that +1 is baked in the fact that the end points at the last one. Right, so that's the usual convention. I don't know for a fact if clexer init follows that convention. But because it's so common, I just automatically, naturally assume that that's what it is. We can check it out, actually. We can check it out, right. So here it accepts input stream end, right. So, and what does it say? Points to the end of the file or null if you use 0 for end of file. Oh. Okay, so you can actually put a null in there. I didn't know that, right? So that simplifies everything, but we want to probably figure out how exactly it is used. So let's actually go through the usages. Then it basically assigned to the end of file, right? It's assigned to the end of file. So we need to check how end of file is used. Right. So as you can see, you have the current parse point, and you subtract the parse point from the end of file. And those getting the size of the remain sequence, which actually confirms my hypothesis. Yes, it must be, you know, the pointer to the element after the last one, because otherwise this formula won't work. It's literally the formula that I just showed. Like, it's literally the one that I just demonstrated in here, right? End minus begin, end minus begin. So I just guessed it, right? So because that's usually how it goes. We can go even further, but I think, by the way, since No, we don't really use null termination, right? So we don't really have a null termination in here because the string builder doesn't really append a null terminator. But if it was null terminated, we could have actually put a null in here and that would work as well. Right. Thank you for asking this question, by the way. Thank you for asking this question because without it, I would not look into the source code and I wouldn't discover that you could just put null in here if you use null terminator. We don't use null terminator, but that's a very important thing to actually consider because that allows you to maybe put string literals in here, right? So you can put code in here like that, right? So 35 plus 2 multiplied by 17, right? And then you can put null in here. So, and then you can lex that specific string literal, but we actually accepting all of that from a file. So anyway, right, we have initialized lexa. So the next thing we want to do is to iterate through the lexems. But how do you do that? I don't remember. So see, let me find a function that looks for the next lexa. So here it is. This function returns non-zero if a token is parsed or 0 if it's end of file. Okay. So while we get the token, what do? We're going to be actually printing the token. So we have a token ID, right, which is a Unicode code point for a single character token, less than 0 for multi-character or end of file or error. So code point for a single character points. Okay, that makes sense actually. That makes sense. So we can do lexa token, and if it's greater than 0, we should treat it as a single character, right? So we should treat it as a single character. So this is going to be that, and so we can do just that. So it also uses like a Unicode, but I don't really care about it. So if it's a multi-character, right, it probably uses a very specific ID, right? For example, one of those things, maybe like an ident and whatnot. So identifiers. So yeah, ident. How do we know if something is identifier? But maybe it doesn't really matter. So, well, I mean, it does matter because we do have identifiers in here. So, yeah, we probably gonna have this, and this as characters. And then we're gonna have this as an identifier, print is an identifier, and this is a number. So we need to be able to distinguish between identifiers and numbers, right? So that's one of the things we'll have to do. So there is a clex parser. So that means, here they are. I found them, mother flipper, found them. So we're gonna be distinguishing between clex integer, and there must be identifier somewhere here. Maybe name. Is there something like name? Plus equal character literal ID. Okay, found it. Freaking found it. Okay, that's cool. So, and in here, I suppose we can do something like switch lexa token, switch, and we're gonna have case for clex ID, right? So we're gonna do something in here, and also clex integer, right? So this is gonna be case clex integer, boom. And in case of an integer, how we're gonna be doing that? So this is the lexa. So this is the number, right? So in case of the integer, we can just do d, like so. Lexa, not really token, int. What is it called? Int number. So this is the int number. And for the ID, I'm actually really curious how we're going to be doing that. Probably through stringlen, right? So if I do clex ID, is there any examples on how to do that? So clex token, clex ID. Yeah, there's no really Yeah, it probably stored in a string. I see. It's probably stored in a string. So, and let's go and just do something like this. And as far as I know, you probably want to do something like this, right? Or maybe like this. Lexa string length, and then Lexa string. So that should be basically it. That should be basically, let's try to go to the compilation errors. Store length, I actually accidentally deleted it apparently. So let's undelete that. What's next we have? So none of those things, by the way, are pointers. So I don't know why the fuck am I doing that, but Lexa, Lexa dot. So we're gonna do something like this. Boom. Okay, that seems to be compiled. So let's actually try to run the compiler. And that kind of worked, except, yeah, so for the numbers, it definitely didn't work, right? So that was kind of weird. So, and for the, yeah, but it managed to parse these things, right? So it managed to parse the special characters and stuff like that. But for the identifier, that was kind of sus. So let's actually say ident int and see how it's gonna go. So I'm gonna rebuild this entire thing. It did not. It didn't even print the information. Like it didn't print. Did I fuck something up, chat? Did I fuck something up? So because it doesn't make any sense. Right, I would at least expect it to have this prefix, if you know what I mean. Right, so let's actually remove all of that. Yeah, this is dumb. This is absolutely dumb. Because, yeah. What? If I don't provide any of that, if I provide this, oh, yeah, I'm an idiot. Apparently, it's still bigger than. Okay. So I suppose we are kind of expected to do something like this then. All right. So if it is like we expecting plus, right? We expecting plus. We expecting this. We expecting this, and we also expecting this. The rest of the stuff we can kind of ignore, or maybe even you know, complain about, if you know what I mean. Right, so this one is going to be more like this Lexa token. So that's basically what, yeah, there we go. That makes sense. And these things are still considered identifiers, so that's what's weird about it, right? So they are still kind of, well, I mean, this is because I made them, so I'm an idiot. Yeah, there we go, so this is a character. Maybe even we can call them punctuation signs, right? So that's what they are. And in here for the identifier, right, so we have to do something like this. So Lexa string lex, yeah, string len string, and this one is going to be Lexa int number. All right, we almost did that. Except for the string. And the problem with the string, I can never remember the scene. Yeah, finally. There we go. Ooh, for some reason, this is a cool library. It saves a lot of time, but using it, I keep forgetting how the fuck to use this. Right. It's just like, right, token IDs, and it's just like, why is it so bizarre? Anyway. I mean, it kind of makes sense, right? So it kind of makes sense, but it's not particularly intuitive. Another thing we can do, we can always say, you know, unexpected token, right? So assert 0, unexpected token. We can also provide the location where this entire thing is located, right? So if I'm not mistaken, in the Lexa, we do have the position location, STB location. So, okay, so you can get the location. So this inefficient function returns the line number, blah, blah, blah. Okay, but what is where? What is where? I don't understand what is where, but so input stream. Okay, you start with the input stream. While the input stream is less than where? Is that the beginning? So this input stream must be less than where? It must be less than where? I hate this function. I hate this function. Honestly, it's just like, okay, so let me see. So we have a token, but I mean, it's a very inefficient function, as they say. We have to provide the Lexa. We can allocate the location on the stack. That is fine. Honestly, sometimes like writing the Lexa from scratch is easier than figuring out how to use this library over and over again. I think I already used this thing one more time in Google. Yeah, I think I can just look up how to do this thing. Google, yeah, where is the location? No, I didn't use it. Fuck, and there's no even example on how to. Maybe we can find something on the like, because the library itself doesn't contain any examples on how to use it, because fuck you. So maybe somebody used it on the internet. And nobody on the entire internet fucking used this. Alright. Few words would have saved so much time. But I'm not supposed to complain. This library is free. I didn't pay anything for it. Where first char? Obviously, you dummy dum. Obviously. Thank you, whoever like wrote this. Thank you. Right. Thank you. You saved me some time. Whew. All right. So so this is where. So this is what you're supposed to put here, which is so fucking bizarre. I already passed Lexa in there. Just fucking use it. Maybe it's like you can customize. Like maybe there's a last character or something. I don't fucking know. Anyway. So yeah. So here we're gonna have a path and then lock. Right, so where is the location? It's a number. Line number and line offset. Okay, so let's actually do line number. So and then here we're gonna do a similar thing. The thing is, like, I already used this library before, but I keep forgetting how to use it. I keep forgetting how to use it. It's just like, Lexa is supposed to be pointer. Damn, bruv, like, wrong argument order. What the fuck are you talking about? Get location. You are trolling. No, you are literally trolling. Who said wrong argument order? We need to ban this person. So, oh yeah, that's what you mean. Okay, mods, unban them. Unban them. Alright. No, keep them banned. Keep them banned. There we go, finally. And they're all on the same line, which is perfect. So what I want to do in here, I want to do something like this. Right, so, and here we're going to be doing the offset. Offset. Too fucking long. Number. Finally. Oh, this is horrible, by the way, because, yeah, we probably need to. So the line is already 1 based, but the offset is kind of 0 based. Right. But I wonder if I can just do something like this. Yeah, it seems to be working. So we probably need to do offset slightly different. Lock line offset +1. I'm gonna just like add 1 in here. So hopefully that will work a little bit better. There we go. We are iterating through the tokens, as you can see. Yeah, there we go. We parse this mother flipper. We parse this mother flipper. So we probably don't want that. Look at that. So the only thing that is left to do is to build like a syntax tree out of that scheiße. Out of that scheiße. But I'm already streaming for like 1 hour and I ran out of tea. And you know what that means. You know what that means. Let's make a small break. All right, so let's continue. What we want to do, I suppose we want to start generating some stuff. So essentially, I'm going to maybe just open a file, right, the output file. Maybe I'm going to even have like out path, which is going to be main SSA, right? So the input is main.py, the output is going to main SSA. All of that is hard-coded as for now, but that's besides the point. So this is going to be out. We're going to open out path, and we're going to open it for writing in binary, right? So, and if it fails, of course, right? So we get equal to null. We're probably going to just say, bruh, you fucked up. Nob error. Could not open file as for writing. Right, and we're going to also provide as an explanation. So out path and str error null, and here we're going to just exit with non-zero exit code. So at the end we're also going to do f close. All right, so we're going to close the out. So, and I suppose one of the things we want to do, we want to print some sort of like what is it called, preamble for our program, and preamble is going to be essentially like this, right? So the beginning of the function, right? So this is going to be just the beginning of the function, right? So let's actually copy paste the stuff in here. So this is that and this is that, and we can simply print fprintf all of that stuff in there. Right, so this is going to be new line, and this is going to be fprintf out like this. So this is the preamble of the function that we're generating, and then afterwards we want to kind of close the function. So it's going to be fprintf out, and we're going to just close it like that. Furthermore, we can just test how it works. So file requires stdlib, right? Didn't I have, where's the compilation? Right, so semicolon, there we go. So main.ssa, there we go, right? So this is what we have in here. So we generated like an empty function, though it probably would make sense to also return something. Right, so it's gonna be 1, 2, 3, 4, return 0. We don't really have to put a semicolon in here, right? So let's go ahead and just do that and open this. Forgot new line. That happens sometimes, sure. Let's revert. Boom. So, and we're going to be generating the code in here somewhere. So I suppose we need to maybe start parsing things. Right, so we're going to have two kinds of maybe expressions, right? So let's create enumeration that is sort of like a tag for an expression, right? A tag for an expression, and that is going to be essentially maybe expression kind. And so if we look closely to what we have in here, we have maybe 3 kinds of expressions, maybe actually 4. The fourth kind of expression is a number, maybe an integer, right? So we can call it an integer. Then plus operation, multiply operation, and function call, right? And function call. So essentially like all of these things. So this is going to be an integer, then plus, then multiply, and then fun call, right? So these are different kinds of expressions that we're going to have. So, and then we're going to have some sort of like a tagged union, right? So, but I like to have them as structures. So essentially here we're going to have kind and then the kind in here. And then the second field that I like to do for the expressions in C is something that I call expert as. And this specific expert as is already a union. It is already a union, and it could be one of those things, right? It could be an integer, right? So I don't know. It would be better to actually call it maybe number. So let's actually call it like a number, right? So then you could have maybe expression struct expression plus, right? Struct expression plus. So it's going to be implemented later, right? So to do implement. And we're going to put it like this. So it's going to be plus, plus. And it is a union. So the reason why I like to do it like that is because it allows me to do something very cool, right? So I can have an expression, right? So, and I can check the expression's kind. I can check the expression's kind. Is that expression is a number? If it is a number, I can say expression as number. And I can view that thing as a number. So it's sort of like a tagged union, right? So this is the tag and this is the union. It's a 2 separate sort of like fields. And syntactically in C, it looks kind of nice, right? So expression as number, or if this is a plus, I like to do expression as plus. So this is sort of like the pattern that I developed for myself as I was programming these kind of things in C. It's a little bit cumbersome when you define all of these things, but once you have them, they kind of make sense, right? So they do kind of make sense, right? So, but this is a C programming language where you kind of have to do this kind of stuff. So yeah, maybe we can even have like, you know, a single expression kind in here, which is called bin op, right? And this one is going to be expression bin op. And in here we can have bin op kind, right? And bin op kind could be 2 things. Expression bin, like bin op kind, so bin binary operation, bin op plus multiply. So, and in here we can have like left and right things. Expression left, maybe left hand side and right hand side, right? So this is bin op essentially. This is bin op. So, and here we're gonna have bin op. And the last one we want to have is expression fun call, right? So fun call. And the fun call, what is it going to be? Expression fun call. Expression fun call. So it needs to have some sort of a name, right? Some sort of a name. But to keep things simple, maybe we need to, yeah, let's actually be very, very much specific. Instead of fun call, let's actually call it print. I think it's going to be a little bit easier to work with, because if you're gonna do fun call, right? If you're gonna do fun call, you need to have a name, which is gonna be probably some sort of a string, maybe a string view, right? It must be a name. Then you have to have arguments, and arguments are probably gonna be expressions, and that means you need to define expressions as the you know, the dynamic array, right? So that's going to be another thing that you have to think about, but maybe we can do that, right? So it's not that big of a deal, right? So, and also it has to be capacity, because we're going to be reallocating all that shit all the time. Yeah, if we're going to have fun call, okay, so if we're going to have fun call, so how difficult it is to have a string view, because string view is basically going to be identifier, right? So it's going to be identifier. So we'll have to copy that string view somewhere, right? So we have to put it somewhere. So maybe string duplicate and whatnot. We can try to do that, but yeah. So that's basically the syntax, right? So you have expressions, expression kinds, binop kinds, and that's like literally AST, the entirety of the AST. Right, so that's how we can kind of define that in C. Right, so obviously it's not going to compile, right? So because there's some definition missing, stuff like that. So expression, for example, here. So probably we want to forward declare this specific thing. Right, we want to forward declare. And let's actually find expr like this, and let's put it somewhere here. So let's actually put it somewhere here, and let's recompile this entire stuff. So this has to be the kind, the string view. Well, right, so but again, we're using string view from knob maybe, right? So okay, so all of these definitions do in fact compile, right? All of them do in fact compile. And so yeah, we can start with defining like recursive descent parser, right? And the idea of recursive descent parser is going to be the following, right? So essentially parse expression. We're just parsing a certain expression. We're going to be accepting stbc lexa as the lexa. It's actually just stb lexa as an input. And I suppose we can accept the pointer to the expression as the output, right? Because I want to reserve a result for indication and error, right? So for indication and error, so then it will be easier to actually unwind the entire recursive process, if you know what I mean. Right, so here we parse in the expression. And to be fair, we can actually hard code precedence as of right now. We can hard code the precedence as of right now. So, and for each individual sort of like thing that we have in here, we're going to have a separate parsing, so to speak. So for instance, we're going to probably have separate like parse plus, right? So it's going to be parse plus, maybe expr plus for the consistency. And this thing is going to maybe accept sort of like a plus in here, right? So here we're going to return false. And here we're going to have expr molt, right? Expert molt, and this is going to be also molt and molt. So, and we could have like separate function for parsing integer and parsing function calls, but integers and function calls are so-called primary expressions. If you take a look at the Pratt algorithm, there's a BNF in the Pratt algorithm, I think. So this is not particularly great way to actually demonstrate this thing. So there was a, I think it was a precedence climbing. Operator precedence climbing. Okay, so was it? Yeah, there we go. So that's how we usually do that, right? So expression, right? So you have like a root expression. You have a root expression. Then root expression is equal to the expression with the lowest precedence. For example, equality expression. Equality expression is additive expression with a higher precedence on the left, equal, not equal, and additive on the right. And additive is multiplicative, which is you know, higher priority, and multiplicative is primary multiplied by primary. Primary is sort of like an expression with the highest precedence, if that makes any sense. So as you can see, you sort of recursively go down and sort of climb the precedence. So in that case, usually people clamp together things like numbers and function calls as the primary expressions, right? As the primary expressions. And because of that, we're going to have something like, I don't know, parse primary, right? Parse primary. And it is going to essentially accept maybe just a regular expression, right? So maybe we're going to call it primary. So there we go. There we go. All right. So when you parse an expression, the first thing we want to parse is, in fact, you know, the plus, because it has the lowest precedence. So to be fair, parsing a plus may actually result not in the plus itself, but rather in its own left-hand side. So it's better to actually accept just an expression in here. Yeah, so let's actually accept just an expression in here. And for the consistency, let's call this thing expression as well. So here we just return parse expression plus lexa expression. Okay, cool. So in the plus, we're going to be parsing multiplication as left-hand side. All right, so we provide the lexa. That, actually not that, but we're going to have expression left-hand side. Right, so this is going to be left-hand side, and we just pass left-hand side in here. Right, so that's what we do. Then, I suppose, we need to pick into the next token. Right, we need to pick into the next token. But how can we do that? Can you pick? You can't pick in this, really? Get token. It doesn't have look ahead. Fuck. Is it a seek? What has seek? Okay, wasting my time. All right, listening to chat again. So it doesn't have look ahead. Fuck, it fucked me up so badly. It fucked me up so badly because like look ahead is a special feature that you have to implement, and we do need look ahead, like at least one token ahead. So that is so fucking bad. But essentially, what we have to do, we need to somehow check the next token, right? So check token, and if that token is equal to plus, right? Somehow, so I think it's a collects, maybe just like plus, right? So maybe just plus, and so if it is, we have to introduce right-hand side, right? We have to parse right-hand side and effectively put those things together, right? So we have to put them together. We can create a new expression, right? So we can create a new expression, right? So let's call it plus. So and its kind is going to be expression plus. And so we actually introduced expression binop, right, didn't we? So it's going to be binop. So then binop equal to that, and the kind of the binop is going to be expression plus. And here you have left-hand side and right-hand side. But the left-hand side and right-hand side has to be pointers, and this is not going to work like that. You can't just do it like that, right? Because left-hand side and right-hand side are allocated on the stack, right? As you can see, we allocated them on the stack. Which kind of means that we probably want to allocate them dynamically, right? So it's going to be malloc size of expression, right? And of course you want to probably assert that this thing is not equal to null. Since we are allocating the expression that we plan to return on the stack, since we're doing that, we might as well return it like that and indicate an error with a null, right? If and some sort of an error has happened. If some sort of an error has happened, we just return null, right? We just return null. But that leads to a very troublesome memory management. Right, because essentially you allocated this thing and then an error has happened while you parsed a sub-expression. Now you have to deallocate this thing, right? But you know, after developing this kind of application for quite some time, I realized that let it leak, let it leak, let it leak, oh let it leak. Memory cost pennies, let it leak, do, do, do. Just buy more RAM, just buy more RAM. Essentially, one of the things we can do, we can use arenas. We can use arenas. So arena allocator is actually a pretty cool idea. So let me actually show you arena.h. I think that's what it is. Oh, it's not .h, it's without the header. So, and yeah, so I'm gonna actually copy paste it in here. So let's put it like this and in the description. So the idea is that you're allocating the memory not on a heap, but in a special place that you control, right? A special place that you control called arena. So you allocate everything into the arena. And after you are done doing your thing, you allocate everything that you put into that arena at once. So that way, you never have to think about when to allocate, when to deallocate. Just fucking let it leak. Just allocate, just, you know, fire and forget as much as possible. And then when you're done, regardless of whether there was an error or there was no error, you just deallocate everything at once. Right. So, and that's what we can use in here. So we can just like go there, right? So, yeah. So this is the arena that I implemented quite some time ago for myself, for my needs, and I might as well actually use it. So, because why not? And as far as I know, arena allocators are really like popular among the language developers for that exact reason. So then you can just recursively traverse and allocate things and don't think about them and just allocate everything at once. Right. So let me now introduce another thing in here. So this is going to be arena, and this is going to be arena. Okay, so here we can allocate maybe global arena, right? So arena parser arena, and we're gonna just like do it like this. So it's gonna be static thing. So that's it. You don't have to initialize anything. This thing being 0 initialized is already you know, initialized, and you can right away use it, right? So arena alloc, right? So you basically provide the pointer to the arena into which you want to allocate things, and you provide the size of the object that you want to allocate, and it will return you the pointer to that thing. Right, so where's malloc? So we can do arena alloc, parser arena. I'm going to provide the pointer. So we don't even have to do assert. I remember arena alloc does assert for us. I think it does, yeah, I think it does assert for us. So there's a new region, right? So it actually linked list of regions. And yeah, there we go. So it calls malloc underneath, right? And then underneath, yeah, this is how we say it. And then if it fails, it just asserts it, right? So we don't have to even worry about that. So that's actually kind of cool. So you can just do it like that. And in here, you can just do it like that. So that's it. That's pretty cool. So and then once we're done, we can just do, actually we can even do something like arena reset. And that way it doesn't deallocate allocated memory, but it allows you to reuse whatever it already allocated. So there's two functions, arena reset, which just resets all of the regions pre-allocated. So the next time you allocate within arena, it will just reuse them very quickly without actually calling to malloc, right? Or you can do free, and it will actually free them. It will just call free for them. And in here, we can actually have several backend implementations, right? So you can use libc malloc. As far as I know, you can also use virtual alloc. I don't remember if we implemented mmap, right? So Linux mmap. I think we didn't. And there was also an idea to actually implement a backend for WASM, for WebAssembly. Yeah, we also didn't implement it. So there's two backends for this arena that are not implemented. But somebody actually submitted virtual alloc, right? So yeah, we do have, do we have, well, wait. Current platform, yeah, we do have a virtual alloc. So on Windows, you can directly use virtual alloc. It has a Windows support, but it doesn't have a Linux support. So it's actually kind of funny. But anyway, so that way we don't have to think about it too much, right? So just like don't freaking worry about it. And we can just do it like that. And at the end in here, we can just return LHS. All right, so we can just return LHS. So funny enough, we can check the token, and if it is equal to that, we have to, yeah, we have to sort of like get the next token. So, and the funny thing in here is that for the multiplication, we kind of have to do the same thing, except with the multiplication operator, And here we're going to return expert like so, right? Expert like so. And since we're started to do this very much dynamically, we might as well actually continue doing all of that. So you see how I don't write like a final signatures, right? So I just write the code, and as the requirements and problems arrive, I modify things and adjust things. So initially I wanted to do return Boolean, but now I see that it would be better to do it like that, right? So the code constantly changing, it's adapting and everything. And for the multiplication, so here we're going to be actually checking for multiply, but instead of calling to like a lower, like actually higher precedence, we're going to be calling directly to primary, right? So we're just calling directly to primary. And within the primary, we're going to be already parsing the either function calls or the numbers, right? So all of that is not going to compile because we cannot check a token in Alexa without actually, how to say that? Without actually taking it out, right? Without actually taking it out. And that's a kind of a problem. So what I'm thinking is that maybe we're going to prelex everything, right? Maybe we're going to prelex everything, just iterate through all of them and collect them into like a single thing. Then just use that when you parse things. Right, so we can have maybe a notion of a lexem, right? So, or token of some sort. So this is going to be lexem, right? So also call it like that. And we're going to have it as a kind, and maybe we're going to use the same kind as in here, right? So where is the token? So yeah, it uses long, right? So this is going to be the token, right? So maybe we can also call the token. Right, so they have the same name as in the library. So this is going to be that. But on top of that, we need to also have like an identifier, right? So some sort of an identifier. So we can have string and string length. So definitely here we probably want to have int number, right? So this is going to be int number and the string stuff. So for the string, it's a little bit annoying because on the next call to get the next token, the pointer to the string constantly being invalidated. It is constantly being invalidated. So that means as we get a new token, we have to so essentially copy it. But we can copy all of that, you know, all of the strings into this arena. Yeah, we can actually copy strings into that arena. So I wonder if arena has convenient functions to do that. It has quite a few interesting functions, actually. I think it's... no, we didn't really have strdupe or something like dupe. Nah, it doesn't have that. So, but we can have, we can create some functions to sort of help. Anyway, so as we iterate through all of that stuff, so we can actually keep track of other things. We can keep track of the path, right, of the file path, and row and column, right? So we can have row and column. So, and all of that is very useful because it's a location that we can use in the future and stuff like that. So, and since it's going to be a collection of those lexems, right? So it's going to be a collection of those lexems. We might as well do something like this, right? So we can create a dynamic array of them. So this is going to be basically items. Then we're going to have a count. So this is going to be count. And then it's going to be a capacity. Oof. All right. So this is a little bit annoying. But it is what it is, and it isn't what it isn't. So let's collect all of that into the array of tokens. Lexem lexems. So we initialize it like that. We just initialize it like that. Just initialize it like that. So if we encounter one of these things, what do? We create maybe a lexem that is going to be like this. All right. So it is going to be, we're gonna assign the token regardless of anything. So the token is gonna be equal to that. Right, the token is gonna be equal to that. If this is one of the tokens, we might as well also right away define the path, then row as the line number. Right, so this is the line number, and column as the offset. So we basically defined majority of the stuff here already, right? So basically defined majority of the stuff here already. And now we need to, yeah, so in case of these things, we don't have to do anything. That's basically done, right? That's basically done. In case of an ID, we have to copy the string len, right? So essentially we have to do lexem string arena alloc parser arena, there we go, parser arena, and we need to allocate this amount, lexa string len. So after that, we're gonna copy into this thing. All right, so we copy in this. Can you see shit, by the way? You can't see shit. All right, and how much we wanna copy? We wanna copy this amount of stuff, and then we are effectively assigning string len to that. So that's how we're going to be doing that. So we're allocating all of that into that arena specifically. And in here, lexem int number is going to be equal to lexa int number. There we go. So in here, assert unknown token. So it's we should probably report this thing, but I don't want to do it right now. Anyway, so after we created a lexem, we have to do nob da append, and we're appending all of that into lexems. That specific lexem, we're just like copying it into that, and we basically pre-lexed the entire file, right? So we have all of the lexems, and in fact, that allows us to look ahead as much as we want. So that's actually pretty cool. Right, so, and we can maybe even check that. So I'm gonna go and try to compile that. It's not gonna compile because it's gonna have quite a few compilation errors. So let's actually go through them. So parse primary, right, it's defined. I don't really know why. Oh yeah, so basically that specific function does not accept any pointers anymore, right? So it doesn't accept anything. The next one, yeah, so there's no such thing in here. There's no such thing in here. So as of right now, I would like to maybe put false in here. So I just want to make this code compile. All right, I don't really care about this code that much, but I just wanted to compile. So bin op, so this one is really interesting because you have to do as, right, as bin op. So I'm programming in JavaScript, by the way, chat. I'm programming in JavaScript. Do I look like a JavaScript programmer? So this is binop plus. So now we're parsing that, so here we don't have to accept that. Here we're going to be essentially something like this. So this is false. So I'm just going to the compilation errors. You see, I'm not afraid of compilation errors. One of the skills that you have to develop as a software developer is to stop being afraid of compilation errors, right? So what I did, I essentially laid down the idea, the high-level idea that I had, and only then I started to go through the compilation errors in here. Right, so there is a semicolon, and there we go. It finally compiles, right? So I sort of like roughly outlined the idea that I want without caring too much of the compilation errors. And then I just went through the compilation errors and fixed them up and sort of stitched them together and clean everything up. So this is why, by the way, I don't like the LSPs or the systems that constantly remind me that I have some sort of errors. Because I have this phase of the development that I don't care about compilation errors or even syntactical errors, right? I just lay down the idea that I have, see what kind of works in my head, and only then I focus on the actual compilation errors. And why it is important for me, because sometimes I make up shit. So here I made up some sort of a fucking function that doesn't make any fucking sense and just doesn't exist, and it's just like, this is important for me. Because it's just a prototype code. It's a prototype code. So sometimes I may write in even a pseudocode, right? And pseudocode may not even compile, and that's good, because the places where pseudocode didn't compile are the to-do points, right? You're basically using the compiler as an assistant to go through the to-dos. So you have a syntactical error somewhere, that's a to-do to actually go through, right? So you potentially put some sort of syntactical error in there, so the compiler will tell you to go back there at some point. So you want your editor to let me cook mode. Yeah, exactly. So let me cook phase of the software development. And to be fair, there is a very weird trend in software development tools that is present like everywhere. You can see that in all of these LSPs and linters and checkers and borrow checkers, especially in Rust, right? Especially in Rust, they all treat the code that you write as a production code, as the final code. All code is production is very toxic idea, honestly. It is extremely toxic idea. Like, the code that I write, like, I didn't finish writing my code. Your code already breaks the build, motherfucker. We need to punish you. We need to fucking punish you. We need to punish you. We need to put like all red lines all over the space. Like, dude, let me finish my code. That's a very toxic mentality that a lot of development tools adapted. All code, even the one that you didn't even finish writing, is a production code. And if it doesn't compile, we're gonna punish you. This is really bad, in my opinion. It's probably one of the reasons why people hate programming, right? Because they're constantly being punished for what they write, even if the code is not finished. So I don't know, man. So, how are we going to be approaching all of that? So essentially all these passes are not going to be accepting the lexa anymore. They're going to be accepting lexems. Right, so they're going to be accepting lexems. So an interesting thing, we're going to be taking this, how to say that? Because I also need to keep track of what lexems I consumed and what I didn't consume yet. So, but here is an interesting thing. Since this thing is my own structure, right? So the reason why I added those specific field here, this is a very cool thing, is that then I can use it with this di append macro. It's a special macro. It's a special macro that expects these specific fields, right? So if we go into knob, di append, right? So where is the di append? It's somewhere, knob di append, yeah. So this is how it works. So it automatically searches for all of these fields, count, capacity, and items, and reallocates the items if the capacity was exceeded. So it's a very convenient way to do dynamic arrays in C. But the advantage of that is that you have your own custom structure, and you can add more fields in here, and this macro is not going to break because it doesn't give a fuck about these things. So because of that, I can add additional fields like pose that indicate what's the current lexem that we are currently handling. So this thing acts simultaneously as dynamic array and a simple lexer that just iterates through the lexems. So that's pretty cool, isn't it? So, but I want you to actually check if this entire thing even works, right? So let me maybe add a little bit of the, you know, debug information, right? So let's actually go back to stb lexer, and we're gonna accept the lexer. Right, so this is something that I really wanted to quickly check. So I'm gonna break on main, I'm gonna actually run, and let's just see. So I'm going to go here, right, boom. So, and let's take a look at some of this stuff, right? So we have lexems, right? So here they are. We've got 8 lexems. We've got 8 lexems. We can even take a look at what they are. So it's going to be items. We're going to dereference those items. I'm going to take exactly lexems count of those items, and that didn't freaking work because I made a fucky wacky oopsie doopsie. Ooh. All right, so what do we have in here? So we have token 260, right? So we can even take a look at what it fucking means, mate. 260. So there's no such thing, but I mean it's an identifier, right? So I know that it is identifier. So then you have 40, which is probably like an open parent. Then you have 35, right? So you have int number 35, int number 17, int number 2, and so on and so forth. So basically we pre-cached all of the tokens. We pre-cached all of the tokens so we can work with them, right, in a more eager manner, right? Not lazily, like extracting them one by one, but we just pre-cached them, and now we can look ahead as far as we want, right? So we can now look ahead as far as we want, not just one symbol ahead, but as many symbols ahead as we want, which is kind of cool, which is kind of progress. So anyway, so how are we going to be approaching all of that? So if I want to check the current symbol, right? So here I'm parsing expression plus, and what I can do, I can just do, I can accept lexems. So first thing I need to do, I need to check whether we're not at the end. If lexems pose is less than lexems count, that means we have some lexems in there. And lexems items at lexems pose token equal to plus, that means we have to continue. So that's basically what we do. That's basically what we do. We need to change lexa to lexems, and there we go. Right. So we check whether we have something in there, right? So, and then we check what at that specific position. If that thing is plus, we're Gucci, we're Tamaguchi, we can continue. So this is for plus. So it allows us to look ahead, as you can see. All right. And what's interesting is that once we notice that it's plus, what we can do, we can actually increment it by 1. So we kind of consumed that token. You see what I'm talking about? You see what I'm talking about? So we just consume that token. So pose plus 1. So, and we need to repeat that for the multiplication. Might as well, by the way. Right, so just copy paste it, and every time we encounter plus, we can do molt. Right, so this is molt, this is molt. Here, this is the multiplication, and as we go down, right, we actually don't go into the multiplication, go into the primary. There we go. So this is one layer lower, And the most interesting thing here, right, is probably the primary, right? So this is going to be the primary. And in the primary, we only care about 2 lexems, right? So first of all, we can do the following thing. If for some reason we ran out of tokens, we probably need to indicate that. We need to probably indicate that. So we can say something like error expected expected number or identifier, but got the end of the file. And then we just return null out of that. And here we also return null for now. Right. So that's very interesting. So we checked that we at least have some lexems in here. Now we can switch upon different kind of lexems, right? So this is going to be items, right? And then this is going to be the position, and we take in the current token. And what kind of situations do we have? We have a situation clex number, right? So this is a clex number. So it's going to be one thing, identifier, or others. So in the case of others, we just have to throw an error. But it's pretty straightforward. So we can actually do the following thing. We can do lexem, and just take a pointer, so it's not that huge of a thing to look into. So then later we can quite easily just get the file path, and the row and the column, saying that unexpected token, right? Unexpected token. And where we can get all of these things? We can get all of these things from path, right? So row, column, and we can even return null in here. There we go. We're almost finished parsing this entire thing. So we only need to parse the numbers, right? So if it is a number, what we have to do, we have to just allocate the expression node. So we already know how to do that. So we can just do num. Here we can do, by the way, this one is interesting. Speaking of, in these things, we have to also allocate all of that shit in the dynamic memory. I didn't think about that. Right, so expression plus, let's allocate that. Everything is going to be in dynamic memory. But then we probably can do something like clitoral. Let's actually, yeah, we can do clitoral situation in here. Furthermore, yeah, something like this. And then we can just return plus. Maybe even... Can I do... Nah. So we can just do return plus. Yeah, something like this. Something like this. So this is going to be plus. Benop, blah, blah, blah. So this is a right-hand side. Yeah, I think that's how it has to be done. Right, I think that's how it has to be done. So in here, we just do that. And then we can do another clitoral situation in here. And then we can just return mult. So that should be all right. That should be all right. It's pretty dynamic, but I mean, that's fine. That's C for you, meine Freunde. So kind is going to be expression num. Number. Num is going to be as number, please. Thank you. Lexem int number, and we just return that. And by the way, so we already copied everything. Okay, so I'm really happy with that. So expression, so identifier. Okay, identifier is rather interesting. So it has to be a function call then. Arena allocator. So yeah, for the arena allocator, for the function call. So what we have to do? We have to do function call. Kind expression fun call, right? So this is going to be expression fun call, and then as fun call, we're going to have args. So do we have express? Yeah. So here they are. So that means we need to basically parse arguments. Maybe we're going to introduce a separate function, parse args. Yeah, parse args. By the way, every time we sort of consume the token, I think we have to do +1 in here and definitely +1 in here, right? So we consumed that token. Might as well even do +1 in here one time. I don't care about it anymore. So parse args. So parsing the args for the lexems, and that should not, well, I mean, yeah, we're gonna be appending the args in here, so it would be nice to actually take it by the pointer. Take it by the pointer. If it's not equal, just return null, and that's about it. So this is probably the last thing that we'll have to implement, parse arguments. So yeah, so let's go ahead and just go to the compilation errors. So collects undeclared. Is it collects number? So collects integer int lit. Okay, so it's actually called int lit. What's next? It's ID. What's next? Parse args. All right. So we're gonna do boolean, and we accept lexems in here plus the pointer to the arguments which we're gonna be modifying. What else do we have? Lexems. What else? Sems. Plus. And in here we have to accept lexem. If we parse in, yeah, so if we parse in the expression, we have to return it like that. Lexems. Parsing the lexems. Okay, so that seems to be compiling. So the last thing we need to do, we need to parse the arguments. To be fair, maybe I'm gonna parse only one argument for now. Right, because I don't really want to deal with the things. So it would be nice to have a function that basically expects a certain kind of token, right? So if expect token lexems collects, maybe just something like this. If this token was not encountered, right, something else was encountered, we should probably return false, and something like this, right? And after that, we can just take one arg. And by the way, if we're going to be having like a list of expressions, we are allocating them as pointers, so it makes sense to actually treat them as pointers. So the thing we can do, args, knob append, args, parse expression lexems. Right, though this thing may fail, so it's going to be expression a single arg. If arg is equal to null, we're going to return false. Otherwise, we're going to append it to the list of args, and then we're going to just return true. So that's how I want to parse it. So we expect open parent, then we parse a single argument, we check that the argument is not bogus, then we append this thing to this list of arguments that we passed in there, then we expect the closing thing, and then we return true. So the last thing that we need to implement here is expect token, which returns boolean, accepts lexems, and the token itself. Maybe more like, yeah, expected token. So it's pretty easy. First of all, we need to check if the lexems even have anything. So basically the count. If it's actually greater or equal, we have to throw some sort of an error. We already thrown an error, right? So we can say expected. I know we can say expected token L, and we can just do token, but got the end of the file. So it's not going to be human readable, it's going to be just indices and numbers, but I don't want to spend too much time on human readable error messages right now. So lexems items, right, so let's take the position, let's take the current thing, and let's take the token, and if it's not equal to the token, actually here we have to have false. We're also gonna do the following thing: expected token that, but got that, and again it's not gonna be human readable, but that's fine for now. Right, we can always look them up, and after that we can just return true. Right, we can just return true. So that's about it, honestly. But if we expect the token, if it yeah, we should probably directly modify the pose. So one of the problems here we may encounter is that we may forget to increment pose at some point. Right, so we checked for that. So we check for this, we consume the token. We parsed these things and we append it to the args and we checked for that. So we support only one argument right now. It's easy to add more, but I just don't want to spend time on that. So in the primary, we check the first token, right? So we consume it. So here we just add it and that's fine. So for the function calls, we just do that. Then we parse the arguments and arguments do everything. So here everything's fine. So for the multiplication, we consume the token, everything's fine. For the addition, we consume the token. All right, and that's about it. I think that's the entirety of the parser, actually. I think that's basically the entirety of the parser. And by the way, here we may want to maybe print the location, right? So let's actually do lexem like this. Let's print the location, lexem token. Lexem token, and here we're gonna have the S, the D, and the double D. Lexem path, lexem row, lexem column. There we go. So let's go through the compilation errors. What do we have? Lexem s. What else? Lexeme. It's usually this kind of shit. It's not really that important. Parse expression, we need to forward declare it, by the way. Right, so it needs to be forward declared here somewhere. Parse expressions, actually it's not that, it's that. Nope, DA append. What else do we want? Boom. Cool. So we basically learned how to parse everything. So let's actually try to parse the expression, root, and this is going to be the expression. Parse expression lexem s, and see how it goes. If root equal to null, which is going to return 1. Let's see how it goes. So it doesn't like that because we have to pass it by a pointer. There we go. So let's go into the debugger. So we did it one more time. Yeah, that was fine. So let's break it main and run this entire thing. So I'm going to stop somewhere here and I'm going to continue. So let's take a look at the lexems and see how many of them we've got. Lexems. Right. So we got 8 of them. Cool. Let's take a look at the root. Root is not known yet because we have not run this entire thing. So I'm going to step once and it segfaulted, right? So that's actually kind of cool. So it did in fact segfault. So it segfault at strlen. So let me see. It was trying to print something. So expect tokens. Yeah. And it didn't like something. It's a wrong. Yeah, I did the same mistake again. God damn it. Okay, so let me restructure this entire stuff. It's actually kind of cool that I did all of that in the debugger, so I think it was very beneficial. Yeah. Break main, run. So let's go here. Then I'm gonna step once. Okay, so expected but got. All right, none of that makes any freaking sense. I should have actually expect. L. Yeah, is that? It has to be LD. Yeah, all of these things has to be LD. I don't know why I decided to make them like that. All right, so the next one. Can I kill and refresh a couple of times? Break at main. Run. Do I still have these things? No. Okay. Yeah. So expected but got 42. This is too much. This is some sort of a bullshit, I'm telling you, actually. I'm actually telling you, bruv. How did we end up here? I don't know. So expected 41. So maybe we can actually break at expect tokens. Maybe we can break at expect tokens. Right, and maybe we can just go in here. So let's continue. So that didn't really work. Now, let me see GF2. Okay, so run it. What we've got. So we can take a look at the lexems and token. So we're parsing the arguments, which does in fact make sense, right? Does in fact make sense. All right, so I'm gonna continue. So 41, it expects 41, that's fine. We might as well observe what we've got in here, right? So there is a position. Yeah, after 5, something bogus has happened, right? So it jumped very quickly to 5, which doesn't make much sense to me, because if we take a look at the main pi, right, 1, 2, yeah, it jumped very quickly there. So definitely something with the expression, and I think I know what exactly going on. I forgot to return phone call afterwards. That's what I forgot to do. So it was basically, yeah, it was returning null, and it thought that it couldn't parse this thing, even though it could parse this thing. It was reported as it couldn't. So that's pretty cool. Okay. So let's try to recompile this entire thing and maybe even restart. So GF2, break main, run. So let's actually continue. And can I step once? It still actually causes that. That doesn't make any fucking sense. All right, so I think the time has come to actually go through the entirety of the compilation, right? So because that would, yeah, so that error should have went away, but it didn't. So let's go through the whole compilation, right? So let's break main, let's run. So let's just continue and step, boom. That doesn't make any sense. Like, why did I do it like that? Yeah, I'm an idiot. So it's funny how the compiler always forces you to go through your stupid code and just think about it more thoroughly. Right. So essentially, I don't know why I was doing it like that. Because that's what I wanted to write instead. Right. So that's what I wanted to write instead. And in here, because I changed the way I report errors and stuff. Right. Might as well maybe do something like this. So then here we're allocating a new stuff. So this is multiplication. Like this. Like this. So yeah, there's only one allocation. So this is fine. LHS, RHS. Then the only allocation here. Here everything's fine. Here everything's fine. I hope I caught the last one. I hope that was the last one. Okay, GF2, break main. Alright, so then go here. Continue. Finally. Alright, we're good to go. We're actually good to go. And let's take a look at the root. Okay, so we have a function call. So that is pretty cool. So kind function call. So if you take a look at the function call, it doesn't have any name, which is easy to fix. But I mean, then you have arguments. And it doesn't allow me to go further in the arguments. Maybe it's a limitation of GF, right? So, but this is something that we can fix. Fun call name. So arena, yeah, this is a fun call ID, and I don't really copy. But didn't I do strings? I could swear to God I was copying things somewhere. Okay, so the only thing I have to do, I have to get that stuff from the lexem. Right, and in a fun call expression, fun call, okay, so fun call name, and it's a data, fun call name data, lexem string, count len. There we go. So if I try to compile that, fun call, as fun call. All right, we fixed that. So that should be fine now. All right. gf2 break main run. So let's continue. Everything seems to be okie dokie karaoke. So root. So this is a fun call name. Count z. Did I fuck up something? Right, so this is a fun call name. So I take that shit from the lexem, from the current lexem. And when I'm lexing all of these things, this is the lexa, right? I'm allocating string length into the lexa. Then I'm copying into lexem this stuff, like as much as I put in there. And I'm pretty sure I didn't fuck it up. Like, I mean, I don't see a mistake in here, unless I... yeah, so that should be cool, because if we take a look at the lexems, did I forget to refresh something? I could have actually forgotten refreshing something. Lexems items. All right, so this is going to be that. At lexems count is going to be that, and the first thing, yeah, here it is. String len 0. Yeah, it's already fucked up in here as it is. I can see that. It's already fucked up in here. All right. So that means the mistake is in here. Interesting. Because that is kind of unexpected. All right. So that is kind of unexpected. Okay. So let me try to actually return 1 in here. So I don't really know what the fuck is going on, but printf clex ID, was it string? Because I'm pretty sure it was. So string len and then lexa string. It's probably something super dumb. I'm like, I feel it. I feel it it is something super dumb. Yeah. Okay, so it stopped working. It stopped working, but why did it stop working? Why did it stop working? Did I forget? So it's the lexa. Lexa told us. So maybe I just did that? No. Man, we're just lexing. We're not doing any... Okay, so this is... Yeah, it's an ID, but it tells us that it's 0. The lexa stopped working for whatever reason. I don't know why. Why did it stop working? Is that because of it, I'm trying to mess with locations? Is that why? No, it's not because of that. But this is the error of lexing, and I thought we figured out lexing. I thought we were done with it, right? Weren't we? I'm pretty sure we were done with the lexing and it worked fine, right? And it's just like, now it is not working, and I don't understand what the fuck is going on. Like, what? Okay, it is something absolutely bizarre, because I literally just wrote that code. It worked fine. It worked fine, it stopped working. I have no idea why. So maybe I'm corrupting memory somewhere, maybe that's what's going on. But I mean, I didn't even start doing anything, right? So with the lexems, we can go literally back to before we had any of that. But maybe I can't do that. It is something super dumb, and it's just like very demotivating, because like I know that I can fix it with like one. Yeah. So do I not allocate enough memory for the... All of that is stored within this thing. It's a string store. So all of that is stored there. I really need to start from scratch, basically, right? So that's what's going on, essentially. So let's not do that. Printf. Well, let's start from scratch, I suppose, right? So maybe we'll figure it out. Oh boy, Lexer. This Lexer, I swear, I should stop using this Lexer. It's bad. It's honestly bad. Every time I use it, I kind of waste time. So I should actually just start using my own Lexer or something. So this is going to be that, this is going to be that, and this is going to be the string. So printf character, and we can just do character Lexer token. All right, so let me try to see that. Yeah. Am I just doing that incorrectly? Like maybe this is not how you get an identifier. So there is a pointer. Okay, pointer does make sense. Did I accidentally modify? What is going on? How do we do the identifiers? Right, so collects ID. So when we do collects ID, we create... okay, maybe I just do that incorrectly, but somehow I have a false memory of doing it correctly. This is Lexer, I swear to God. I don't know why I keep using it. I never had any problems with my personal Lexer that I write. Alright, so this one, it just kills me. Line 10. What the? It is it null terminated? How am I supposed... Wait, is it null terminated? Don't tell me it's null terminated. Man, I'm gonna stop using this Lexer from now on. It fucking kills me. Dude, what's the point of having string len if it's null terminated? This is so bad. Like, there's so many confusing things about this Lexer. Like, dude. Okay, maybe this thing is unfinished. Okay, I'm very unjustly complaining. But I mean, I wasted time. Oh my god. So the thing, like, if it's null, it would be nice to have some, like, a little bit of a comment and say, here that says, ignore this field. If it's identifier. Like, how, like, this is so bad. Like, it's, I know that this is, I'm complaining completely unjustified. I understand that, but I just wasted time because of this strange design decision that implies that this thing is always sized and not null terminated. Like, who on earth would think that, okay, in case of identifier, just ignore this thing and use, like... Am I complaining a lot? Because, like, this is really bad design. Like, it's really bad. It's just like, holy shit. I'm sorry. I'm gonna stop using this Lexer. Like, the next time I need to Lex something, I'm not using this one. Not using this one. It's just like second or third time I'm wasting time with it because it's like something that is not properly documented or something confusing that like basically traps you into wasting time. I just can't. I just fucking can't. I'm sorry. So anyway. So here we can kind of substitute for that. We can essentially maybe do something like this. Right, strlen. It's like it's intentionally, it's designed intentionally to fuck you up. Like it's like almost intentional because fuck you. That's what it feels like, honestly. It's just like an intentional fuck you. Maybe that's meant to be like that. I don't know. Again, the author doesn't owe me anything. The author doesn't owe me anything, so. But I'm not using it from now on. It's just like that's it. I'm done with it. But the thing is that you want to have a ready-to-use Lexa. Like I want to have a ready-to-use Lexa. It's like one of the things I want to have. Right, and it's just like this one is a very appealing option because it's just like, yeah, you just like use it. Anyway, I'm sorry. So let's recompile this entire thing. That seems to be fine. Now I can go to gf2, break main, run, and let's go down. Okay. Lexems. Yeah, doesn't matter. So what I care about in here is root. And what do we have in here is the function call. This is a fun call, the name. All right, so you can you see that? So you can see it now. Okay, that's cool. That Lexer, I swear. Okay, I'm gonna stop. Like, I just like don't use it next time. Just simply don't use it next time. Now, what do we want to do? We want to now compile that, right? So we want to now compile that. So let's actually go ahead and introduce compile expression, right? So we're gonna accept the expression and we're gonna just say, oh, compile expression. Simple as that. So, and in here, we're gonna essentially have expression kind, right? We're gonna dispatch on all of the possible kinds of expressions, right? All of the possible kinds of expressions. So let me try to see. I wanna know what kind of kinds of expressions we can have. So we can have numbers, functions, and everything. So essentially, here's the interesting part. Here's the interesting part. So usually if I'm dealing with a stack-based machine, if I encounter a number, I would basically push that number onto the stack. But this is not a stack-based machine. But we can kind of simulate the stack with the variables and the numbers, right? So we can introduce something like a stack size, which is going to be 0. And essentially, what you can say printf. So let's actually indent it like that. So s zu equal w and the number that you're trying to push, like so. So this is going to be stack size and expression as number. There we go. And then you increment the size of the stack. Right. So essentially, you can think of as the stack where the number after as tells you the element on that stack. And you keep track of the size, so you can kind of simulate the stack-based machine with temporaries. You see what I'm talking about? Right, you're simulating a stack-based machine with temporaries, which is rather interesting. By the way, we have to bring that into the output, right? So it would be nice to also accept the output in here, right? So we printed that into that specific file. Now let's actually do the binops, right? So let's do the binops. So here, we also need to switch upon what kind of binop as binop kind. And we have several binops in here. Binop a multiplication. I might as well just do it like that, and plus, right? So this is what we got. Break, break. All right, so this is a function call, and this is another one. Okay, so this is a plus. So how we're going to be doing that? So essentially, we have to take two elements at the top of the stack and add the top one to the one below. That's what we have to do. The top one to the one below. So that means that the stack size has to be like at least 2 arguments. It needs to have at least 2 arguments. So, and how we're going to be doing all of that? How we're going to be doing all of that? We're going to do an assignment of add SZU, SZU. So we're adding the top one to the one below. Right, the one below. So here, the one below is a stack size -2 because we're indexing the elements of the stack from 0. Right. So essentially, if you think about the stack like this, like 0, 1, 2, 3, 4, you have 5 elements. So the stack size equal to 5. So that means the top one is the stack size -1, the one below the stack size -2. Right. So we're adding to the one below. And what we're adding the top of the stack. Right. We're adding the top of the stack. And to be fair, right, it doesn't really matter in which order we're going to be doing that. We can just like do it like that. Right. So to the one below, we're adding them like this. So, and since we consumed 2 elements and pushed a new one, so we effectively consumed 1 element. So we're subtracting 1 from that. We're subtracting 1 from that. And you can repeat that for multiplication as well. You repeat that for multiplication as well. So we're done with these things. And the last thing that is left is a fun call. Right. So the only thing that is left is a fun call. So fun calls right now support only 1 argument. Right. And furthermore, we can even check that maybe expression as name. Right, so we have to use nob sv equal sv parent, so it has to be equal to that. So we're gonna just hardcode this thing, and essentially what do? We have to perform a call to printf. That's how we do that, right? So that's how you do that. So you just do, might as well do something like this. Do printf fmt integer, right? And we're actually, you know, calling the top of the stack, right? So we're calling the top of the stack, and the top of the stack is the stack size -1, and we consumed the thing on top of the stack, so we can just subtract 1 afterwards. And all of these things has to be at the end. So that also means that at the end in here and in like after the code, we need to have the data that looks something like this. So it's going to be out like so. Replace. And then new line. So in here we can just do D, but with a new line. Right, but that new line has to have extra escaping. So that's about it, I think. So it's actually called fmt int. All right, and here we're gonna be doing the compilation of this thing. So we compile an expression. We're compiling an expression, a root expression, into the out. So that's what we are doing. Let's go through the compilation errors. So fun call name. What else do you want? Sv implicit declaration. Didn't I have sv? No, I don't think so. So there is from sister. That's probably what we want to have. All right, and if I now try to run compiler, it created main SSA, and that is so fucking funny. All right, so first of all, we have to put it in here, right? So first of all, we have to put it in here. And one important thing we forgot is that we also need to compile. We also need to compile all of the previous things, right? So if we are compiling binop, right? So we might as well actually first compile left-hand side and right-hand side. So we have to do compile expr out expr as binop left-hand side and then right-hand side, right? So we compiled both of them. So yeah, left-hand side and right-hand side, both of them. And in case of an argument in here, we also have to compile compile expr out expr as fun call args items 0. And another thing we can ascertain here is that args count is equal to 1, right? So we just hard coded all sorts of things in here because we're have a limited time, right? So, and is it going to work? So that didn't work, and this is because the stack size has to be preserved across the calls, right? So this is going to be stack size, like so. So that will require to go through the compilation errors, but I think we can afford that. So here we have to do stack size, stack size. So here it has to be like that. So stack size. So stack size. So that means at the end we'll be able to even check if we even have anything with stack size. And another thing that I think compiler didn't catch is this one. I think this is very important, and since it's a pointer, for the compiler it was very difficult to catch actually. Right. So yeah, now another thing that we also need to, yeah, there's a lot of things. There's a lot of things the compiler literally didn't check, and that's kind of bad. Freaking C, I swear to God, freaking C. So let's actually go manually through all of them. So this is correct. This has to be dereferenced. All of these things have to be dereferenced. All of that stuff has to be dereferenced. So this one, yeah, this one is fine. All right. So are we gonna finally do the trick? Boom. So yeah, it's a little bit of an overkill. It's a little bit of an overkill, but we are using backend and shit. We're using backend, which means that maybe it will optimize everything out. So yeah, we forgot the dollars and everything. So let me quickly do that. It's not even like dollars, it's percents, right? If we take a look at MSA 1 plus 1, SSA, yeah, it has to be percents. It has to be percents. So let's do quickly like this. So, and in here also percents. So let's actually do make minus b. Okay, and then there we go. So that's what we got. That's what we got. Pretty cool. So now, what the fuck is this shit, by the way? This is not bueno, I'm telling you. Yeah, I see what's going on. It has to be... Yeah. Escaping. Freaking escaping madness. Yeah, there we go. So now we're talking. Now we're freaking talking. So the next thing we can do, essentially, we can maybe create like a main. Main SSA. Right, so essentially we do compiler, we depend on the compiler, we just run the compiler, that will create a main SSA. And we can then do main S, main SSA, QBE, QBO, yeah, main S, main SSA. So let's actually try to generate assembly out of that. Invalid instruction, oof. So you can't just assign this shit. Okay, so let's actually go into the documentation. I suppose you don't have to put W in there? I'm confused. Can you just like assign an integer? Like I'm pretty sure you could. Maybe, what if I just don't do that? Like, yeah, it didn't like the instruction, which is bizarre. Invalid class specifier. Huh. Huh? So this was fine. You can't really, you just can't assign numbers to these things? You just can't do that? That is, like, I don't believe that, honestly. So is there, am I missing something, by the way? Am I missing something? Because if I do something very freaking dumb, alright, like add, like I'm pretty sure, or add, examples. Okay. I'm confused. Like, what the fuck do you want from me? Okay, so here it wants that. Really? Fucking really? If I wanna just assign a number to a temporary, how the fuck do I do that? Like, I mean, I understand that I'm probably using that incorrectly. Like, I do understand that. I'm probably using that incorrectly. But if I just want to assign a number to a temp, like, how do I do that? That would have been, that would have made so much sense. So, okay, there is a copy. What is copy instruction? Custom copy. Copy instruction returns the bits of their argument verbatim. Okay. We can try copy. Okay. We can try copy, and when we do that, okay, so this is a copy, and also I forgot the commas. Okay. I do understand that I just do that incorrectly, right? So I do understand that, but I want to do it this way. All right, so we've got this stuff. So this is a main. It actually pre-computed that at compile time. It literally pre-computed that at compile time. That's actually so cool. So it did optimization. And now, all right, so I want to try to do the actual compilation. So we're going to depend on this, and we're going to do cco main.c, and let's just make main. All right, so as you can see, what we did in here, we compiled the compiler, we run the compiler, which generated main.ssa, then we passed main.ssa into QBE, that generated assembler, and we compiled the assembler, and we got the main executable, which we then run, and it prints 69. It in fact prints 69, and in fact, so this thing is modifiable. I can change it to 420, right? I can change it to 420, and I can recompile the whole thing, and if I run main, it is 420. We developed a very simple programming language. It was a little bit hard because I wasted too much time on lexing, so I'm not using this library again. STB libraries are great, don't get me wrong. It's that this specific library is confusing, and it's probably not really maintained that well anyway. That's probably why. it is so confusing. Right. So that's probably why it is so confusing. So, and I suppose maybe it's not meant to be even used at all, just like kind of abandoned and everything. So maybe at some point I will just develop like a library, like Alexa, that I can reuse myself, because like having Alexa apparently for me is a very common thing, because like, very often I just want to quickly throw up like some Alexa to parse something like quickly and not really think about it too much. So yeah. So let me see. Now but what's interesting is that we are only having like one thing in here. You know what would be cool? It would be cool to actually have several statements in here, like this, like several statements. I could say like 69 and 420. So can we add that? Can we add that? That's a very interesting question. We might as well maybe try to do something like this. If I try to compile this entire stuff, so it does not complain, and if I do something like this, it prints only 69, right? So here's our program, it prints only 69. So what we can do, we can actually do that in some sort of a loop, I think. Right, so we can put this stuff in here and say while lexems position is less than the lexems count, we parse a root and we compile it. We might as well keep the same stack throughout the execution. I'm not sure if that's useful, but I mean, we could do that. So, and now if I try to compile that, so it's not a pointer per se. And let's take a look at the SSA. Yeah, so that's the original code that we have. And this is the one. So we might as well actually do 35 plus 17 multiplied by 2. And this one is maybe 202 plus, you know, 10, 2. Something like this. And we can try to run this entire thing and then revert. And that's the generated code, right? So this is the first print. This is basically the computation of the first print, and this is the computation of the second print. So we've got that. And then if we try to run this entire thing, it will print 69 for 20, right? And it was compiled from this code. We already have a simple compiler. So how do you do jumps, by the way? How do you do jumps? Is there any jumps? So there's a GMP. So you have to provide the identifier. Is there any examples though? Unconditional simple jump to another block of the same function. Doesn't really explain, but I would like to have some examples. But yeah, so that's pretty cool. We can even take a look at the, yeah, so in the backend actually computed all these things at compile time as well, right? So it automatically provides all of these optimizations for us. So we don't have to think about that. That's pretty pog. That's pretty pog, I think. All right. So that was interesting. So I think QBE is kind of a cool thing. This particular intermediate language gives me a lot of ideas for my own intermediate language, because from time to time I'm writing my own languages, own programming languages, and I do have intermediate representation, and this particular thing gives me some interesting idea that I would like to personally like explore myself. So yeah, that's basically it for today. Thanks to everyone who's watching me right now. I really appreciate that. Have a good one, and I see you all on the next recreational programming session with Mr. Azuz. Love you. Mwah.